Hello everyone, you're watching the Space Channel. Not long ago, we released a video on nuclear protection and the myths that surround it. In the comments beneath that video, we encountered heavy skepticism about the number of dead and injured we quoted. Many argued that the real toll was much higher. It's radiation, after all. Relying on Soviet statistics is indeed self-disrespect. But what struck us most was a general misunderstanding of just how harmful radiation actually is. As it turns out, the devil isn't always as black as he's painted. So we decided to make a video on how people manage expeditions to the most radiation-polluted spot on the planet. Let's go. On the night of April 26, 1986, the worst technological disaster in Ukraine's history occurred: the accident at the Chernobyl nuclear power plant. That day, the reactor control shift was to rehearse an emergency scenario using a non-standard backup power source. The aim was to learn whether, after the reactor was shut down, the steam turbines could keep spinning on inertia long enough to drive the generator shafts and supply electricity to the reactor service systems in case the external grid was lost or the diesel generators failed. The test went off script immediately. Instead of a gradual power drop, the reactor's output plummeted to zero. To avoid aborting the experiment, the operators hurriedly ramped the power back up, but that process also ran out of control. Power rose to dangerously high levels. The crew took one last fatal decision: pressing the emergency shutdown button and inserting control rods to slow the chain reaction in the core. Yet poorly understood design effects caused the rod insertion to trigger a power spike. Nuclear fuel and the water-steam mixture in the core overheated, and an explosion followed. To this day, there is no unanimous conclusion on the nature of that explosion, whether it was nuclear, non-nuclear, or a series of blasts of different kinds. What is certain is that the reactor core was completely destroyed, the reactor lid was overturned, and the roof of the building above it was blown apart. Part of the radioactive fuel was blasted into the atmosphere, and the burning core was left exposed to the open sky. After the accident, scientists were desperate to know what was happening inside the wrecked core of Unit 4. And there were people, researchers, engineers, journalists, and camera crews willing to find out by going in themselves. How did they endure such expeditions? And what did those journeys mean for their health later on? To grasp how extreme radiation doses might have affected the brave souls who peered into the destroyed reactor, we need to refresh what radiation is and how it is measured. Radiation is ionizing radiation, any emission capable of ionizing matter along its path. Here it comes from radioactive substances. Because of its high energy, it can damage or break DNA molecules in living cells, disrupting vital processes and most often manifesting as cancer. Radioactive emissions are divided into alpha, beta, and gamma radiation, each with different penetrating powers. A sheet of paper stops alpha particles, a sheet of aluminum stops beta particles, and several meters of lead are needed to stop gamma rays. Therefore, because alpha and beta particles penetrate poorly, a protective suit is usually enough to shield you from them. Yet a dosimeter may struggle to detect them, as its casing can block the particles. The catch is that if a radioactive speck enters the body, alpha or beta emissions have more than enough energy to damage tissue. To keep that dust out, you must wear a respirator and seal your face. Still, you might inhale or swallow a particle if the respirator fails, or you touch radioactive dust while removing your gear, so the risk of internal contamination is always present. Gamma rays are so penetrating that no suit can stop them. In their case, what matters is the source's radiation level, measured in Roentgens, and the absorbed dose, measured in sieverts. Gamma radiation is also what dosimeters most often record when checking background levels. Inside Unit 4, after the blast, the building was essentially a chaotic heap of debris, except for some service rooms beneath the reactor that survived. Radiation levels and danger, therefore, vary widely. The overall background is high, but there are isolated, clean islands where radiation levels are lower than normal, alongside hotspots where the dose rate is extreme. If you keep clear of the dangerous spots and move quickly, a visit inside the ruined Chernobyl reactor is equivalent to a handful of chest X-rays. Yet those very hotspots fascinate researchers and thrill seekers who, together with scientists, have ventured into the core to take unique and risky photos and videos. So, what are those locations? As mentioned earlier, the core of Chernobyl's Unit 4 was destroyed entirely. Part of the fuel was blown through the shattered roof into the air, about 5 tons out of the 180 that had been in the reactor. The rest of the fuel, together with everything inside the core, melted in the extreme heat and flowed like lava through technical shafts and pipe chases beneath the reactor. It soon cooled and solidified into grotesque masses resembling stalactites and stalagmites. The largest of these formed directly under the core and became famous as the elephant's foot due to its shape. The elephant's foot and the other fuel masses turned into objects of fascination, even pilgrimage, for scientists and daredevils who ventured inside the reactor. Up close, you could not only marvel at their bizarre appearance, but also watch your dosimeter numbers skyrocket. The first person known to enter the ruined reactor was nuclear physicist Konstantin Chernobyl. In May 1986, he was dispatched to Chernobyl to investigate the cause of the accident. Chernobyl undertook the dangerous task of retrieving instruments from contaminated rooms whose readings might clarify the sequence of events. From that first trip onward, he descended to the Unit 4 shaft regularly for more than 10 years. Based on what he saw, the pattern of destruction and the clumps of fuel, he advanced the hypothesis that the explosion was nuclear in nature and that the cleanup effort was futile. In his view, almost all the fuel had been blown into the atmosphere, making that ejection the main source of contamination rather than the subsequent fire. This position is the exact opposite of the official conclusion, which says that the bulk of the molten core remained inside the building, and no more than 3% of the fuel inventory escaped. Chernobyl worked in the reactor when local dose rates were around 300 roentgens per hour. For comparison, a normal background is about 15 micro-roentgens per hour, 20 million times lower. He never lingered in the most hot spots. He moved quickly through highly contaminated zones and avoided long stays in the reactor hall. He later recalled that he knew the doses he was absorbing, but accepted them as the price of essential scientific work. Official records show his cumulative dose was nearly 100 times the legal limit. Chernobyl did not die instantly of acute radiation syndrome, but its effects progressed over his lifetime. He passed away on 26th of November 2012, age 65, after a long illness. Although Chernobyl was the first inside the core, it is unclear who first discovered the elephant's foot. According to liquidator scientist Alexander Borovoy, the intensely radioactive object was spotted at the end of 1986, when dose rates reached 14,500 roentgens per hour. A human exposed to that level for only a few seconds would succumb to radiation sickness within 2 days. At first, nobody knew what the elephant's foot was made of, and researchers were desperate for a sample. Early attempts were extremely risky. In one account, a soldier tried to chop off a piece with an axe and had to be rushed to hospital with radiation sickness. On another occasion, the mass was shot with an automatic rifle in hopes the bullets would break off fragments. Eventually, samples were obtained and analyzed. Tests disproved the rumor that the lava consisted of the lead dumped from helicopters. They confirmed it is a solidified alloy of uranium fuel, zirconium from the cladding of fuel rods, various radionuclides, and silicon from sand. Over time, the elephant's foot has cracked and crumbled into gritty sand, and radioactive decay has greatly reduced its dose rate. Even so, it remains a few degrees warmer than its surroundings owing to residual heat from decay. In 1990, Victoria Ivlieva became the first journalist to photograph the interior of Unit 4. She worked in awkward protective gear, rubber boots, special gloves, and a plastic suit. Her camera was carried in a plastic bag that had to be opened for each shot. After the trip, the camera was coated with radioactive dust and could be cleaned only with copious wipes soaked in ethyl alcohol. Ivleeva later said she understood the risks. Yet inside the wrecked building, she felt no fear, only a surge of curiosity at being in a forbidden place where others could not go. Another person who visited Chernobyl's Unit 4 regularly was the cameraman Serhiy Koshylev. He first arrived at the plant in 1987 on assignment. Koshylev began filming inside the wrecked reactor during expeditions organized by the same nuclear physicist, Konstantin Chicherov. Initially, to minimize exposure, the shooting was conducted remotely. Rails were laid on the gantry leading to the reactor shaft, and a trolley carrying the camera rolled down them to capture the most hazardous areas. Even so, stepping up to the edge of the gantry, where the irradiated trolley returned, meant absorbing hefty doses. Koshylev worked as a cameraman at Chernobyl from 1987 to 2019, documenting every key stage of the cleanup, from early inspections of the destroyed core and completion of the original shelter, the sarcophagus, to the installation of the new safe confinement and progress reviews during its construction. Although he accumulated doses far above the legal limit, he developed no illnesses clearly attributable to radiation, an exception given how many colleagues' health deteriorated after time inside the shattered reactor. The most famous photograph of the elephant's foot was taken in 1996 by Artur Korneyev, deputy chief of the shelter. He had begun work at Chernobyl shortly after the accident, charged with mapping where the molten fuel had settled in Unit 4. While doing so, he often saw lumps of radioactive material amid the debris, and sometimes had to clear them away with a shovel, or simply shove them aside with his rubber boots to make a passage. Sadly, years spent near fuel accumulations left their mark. In old age, Korneyev developed radiation-related illnesses, including cataracts. The intense rays literally scorched his eye lenses. In the end, for scientists and other specialists, expeditions into the ruined core were not instantly lethal. Protective gear and swift movement let them avoid single, fatal doses. Yet because they had to work repeatedly beside molten fuel masses and contaminated debris, their cumulative exposure far exceeded permissible limits, eventually leading to radiation sickness. One may therefore say that a single, tightly timed visit to the wrecked unit, conducted under strict safety rules, is not deadly for an ordinary person. But it is impossible to tour the confinement and view the destroyed reactor as a tourist. The most dangerous spot a visitor can approach is the memorial plaque to Valery Kodymchuk. He was on duty in the pump hall when the explosion occurred. His body was never recovered, either buried under collapsed structures or vaporized in the blast. The plaque is mounted on the inner side wall of the first sarcophagus, separating the intact Unit 3 from the ruined Unit 4. Even there, background radiation is elevated. Since the full-scale invasion of February 2022, the Chernobyl exclusion zone has been closed to the general public, with only government and military delegations being permitted entry.